Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
We're very lucky today. We're in this room and all the screens are working, so we don't have to sit on top of each other or anything like that. So we should be happy. It's only, what is it, week 3? 4? Gee. All right. Okay, a couple of things to get us started today. So yesterday we were talking at the end about correlation versus causation, and I mentioned some famous examples. So I've added some links to the interesting links part of the Waddle page, and these are basically just for you to look at and read. There's a fair bit of reading, but look, no one's going to make you do it, and I'm not going to test it, so you do it if you want to do it and you don't do it if you don't want to do it. But it's really kind of interesting. So the first one was a tale of imputed causation where really none existed, which is polio and diet. And so the first link I've posted up here is an article by a doctor named Ben Sandler, written in 1951, where he makes the argument that diet prevents polio. So this document was the basis of policy that was presented to the state legislature in North Carolina in the United States. And on the basis of this document, they came pretty close to banning sugary products, in particular soda, soft drinks. So anyway, it's a long read. It's a very long document. Goes for pages and pages. Written in 1951, so one of the things you might look at is the set of graphics that appears inside this paper, and just to get a sense of how life has changed in the 70 years since then, roughly 70 years. So scatter plots were still very popular, as you can see. And as you scroll through, you'll see that, no colour, of course. They couldn't print in colour back then and all that. So, big, long article. And look, this was state-of-the-art science at the time, okay? And, from a historical perspective, these things are really interesting because, these days we have a pretty good handle on the medicine around polio. Polio is eradicated in most parts of the world, although I had a colleague last week who went to the University of Papua New Guinea and needed to get a vaccination before they left because of polio. So it exists in some parts of the world, eradicated here in Australia. It's a dreadful, dreadful disease. A lot of kids got it in the mid-1900s and ended up in iron lungs and really nasty disease. So its eradication's been really important. The drive to eradicate disease is something that medicine works on constantly, and every year there are new diseases and we worry about various things. So this as a policy document was presented to a state legislature. It looked like good science. It established correlation, but made an argument for causation, and that argument ultimately didn't prove to be true. So worth having a look at, and just to see how science gets things wrong sometimes, but that doesn't make the science bad necessarily, and that's an interesting thing to think about. One of the things to think about today in the modern world is where we're headed with questions around climate change, because there's a lot of people say the science is settled, okay, that humans are changing the climate, and you go outside and you know that it's very hot. I did some work last year with the Weather Bureau. There are a lot of people who don't believe in climate change, who do their own science, send it to the Weather Bureau, okay? Very detailed scientific arguments saying climate change doesn't exist. They go back into the historical record of temperature. There was a heat wave in Australia in the late 1800s, hotter than it currently is, and so the argument was it's not getting hotter now, we're just experiencing something like we experienced a century ago, and so on. And, I don't think there's probably anyone in this room who doesn't doubt that climate change exists, because you're all young and you're all seeing it play out in your lives, right? But there are people who don't think so. And the science around polio was somehow similar. And now we've got good medical evidence that brings us forward. Okay, so there's some interesting parallels that we can draw. I don't know if you've heard of Freakonomics. Freakonomics is this rather nice website which looks at all sorts of controversies, usually in economics, but you know, economists think that the whole world is economics, so you can talk about anything. So there's a YouTube video here which talks about the polio versus ice cream story. That's worth watching, and it's a nice take on correlation versus causation, and Freakonomics takes on that topic. So that's definitely worth looking at. So this was a case where there's definitely correlation. By the way, the reason we think that there's correlation here is that both dietary factors, so intake of things like soda and ice cream which contain sugar, they tend to happen more in the colder months. Polio is a temperature-triggered disease, they think, and so it's a lurking factor, temperature, which is probably driving changes in both of those variables. So it's not the case that eating the sugar might cause the polio. It might be a lurking variable like temperature that's actually driving both of those changes. The second thing I've put up here, which is really interesting and worth reading, and look, I'm putting up a lot of reading here, and I know you guys have limited time, but this one is a really fascinating story about Sir Ronald Fisher. I've mentioned Sir Ronald Fisher a few times in this class. He was a funny guy, a genius, almost everybody says, but a mean-spirited man, most people say too, those who knew him. And his story is really interesting. A brilliant scientist, a brilliant statistician. But this story here shows you that no matter how brilliant you are, you can convince yourself of something and then it becomes true, right? And this is particularly, again, salient in this age of fake news, or they say that we've reached the end of truth. Truth doesn't matter. All that matters is opinion. And Sir Ronald Fisher published a lot of science, and again, principled science around the question of causation between smoking and lung cancer. So there's a picture of him, by the way. You can tell he looks a bit mean. I think there's another picture later in this article. Maybe it's not in this article, of him smoking. But anyway, it's a really fascinating story and well worth reading. And again, you read things to learn. You don't read things so you can pass tests. So I encourage you to read it, but I can't make you. But that's worth reading. And lastly, there's a paper here around the question of cigarette smoking and lung cancer. And this is basically the story of what we think is now settled science. We do believe that cigarette smoking does cause lung cancer, and there's good science in behind that. And all of this serves to remind us that, science, we all think of science as this inexorable march of truth. And that just isn't true. Science is pursuing truth, yes, but sometimes it doesn't catch the truth. Sometimes it catches things that are actually wrong, and we think they're true for a very long time, and then there's a discovery which shows them not to be true. Science is the grand human stumble. We're stumbling forward ceaselessly, okay, trying to find out what's true. Most of the time we find out truths. Some of the time we walk down blind alleys, and we walk all the way down blind alleys, okay? Then we discover they're wrong, and we move back. It's the only way you find out, right, what's going on. The role that statistics plays in science is a really fascinating one. Statistics is in some ways the servant of science, because science is mostly about using data to discover truth, and statistics is all about understanding data. Okay? So we're the servant of science in that respect. There's another sense in which statistics is the guardian of science, the preventer of moving down wrong paths, if at all possible. But we can't prevent every problem. And so you've probably heard the expression liars, damn liars, statisticians. This notion that you can use the data to say anything you want. And to some extent that has a basis in fact. You know, people can use statistics badly. In fact, there's a wonderful book, again it was published in 1950 by Darrell Huff, and it's really all about how to use and misuse statistics. And again, it's a wonderful book worth reading. So anyway, I commend these articles to you. They are, again, there's nothing to do with GDA, right? But I want you to, as part of this course, celebrate the diversity that statistics brings and the questions that statistics can have an impact on, right? Because in the end, we're going to learn a lot about graphics in this course, but if you get excited about the way statistics can enrich your ability to find out the truth, then you'll actually be a much better person down the track, and that's the goal for us. So these articles are there. Have a read of them if you want. Ignore them if you want. That's cool too. And see what you think. Okay, so that's today's fun. All right, back to the rats. All right, so yesterday we were talking about the data set, which is the hormone level for these rats and the blood loss, and we were trying to characterise this distribution here. Okay? Now, look, we're going to take again a bit of a journey here. The interim parts of the journey are not methods that I expect you to learn or use, but we're going to cover them fairly quickly. The R code is there if you want to look at it, but you don't have to, all right? When there's stuff that's useful that I think you do need to know, I will tell you, okay? So for the moment, we're just going to go on a bit of a journey. So there's the data, and we're seeking to characterise this distribution. Now yesterday, we kind of got a bit stuck because we don't know what shape this thing is, right? And so my encouragement was to use your fingers in the air to draw what the shape is, and that's pretty good, right? Because your fingers will, generally speaking, follow the middle of the data. And so it'll start off, you know, low and pretty flat, and then as the curve sort of starts to move up, your finger will move up and it'll track the middle of the data. But then as the data gets more dispersed, the middle is a harder thing to define. And if I gave each of you a crayon and a piece of paper with this data on it and I said, draw me the curve, by rights, I probably would get about 150 different curves. And at the left-hand side, they wouldn't be much different because the data's pretty unequivocal about where the curve should be. But at the right-hand side, we'd see all sorts of things. And that really reflects something about your personality. Some people will chase the outliers. Some people will stay faithful to the middle and ignore the outliers. And it's just what's built into your vision as far as what you see. But science doesn't work on the basis of this picture is my opinion about where the line goes, right? And you can't have principled science if you've got 150 different lines and nobody can agree what the real relationship is. So the path that we're on is trying to characterise this relationship, and there are two pathways we can take. The first pathway you'll be familiar with. It's the pathway of parametric statistics. So you've all fit straight lines to data in past lives, and straight lines are very compact descriptions of what's going on. Because when I have a straight line that describes data, I need to know precisely two numbers, the intercept and the slope, and I know everything, and that's it. So I've got 92 rats here. They've each got a data point. It's not a straight line, so that's a problem for the minute. But if I were able to fit a straight line to this, I would replace that 92 pieces of information with just two. Actually, there's a third one, but just two to start with, the intercept and the slope. That would describe the relationship. The third one is the spread, okay, which we can estimate, and we talk about that because we're statisticians. But that's really very compacting of information, right? 92 data points, lots of information, down to three numbers, intercept, slope and spread, and I think I understand it. I can't do that yet because I don't have a straight line. It doesn't look like a straight line, okay? But, you know, if I fit a quadratic, what would the cost be in a parametric sense? Well, a straight line has two numbers I need, intercept and slope. A quadratic only has three, intercept, slope of x and slope of x squared, okay? And so it's still a very compact description of data, and I could use it. If I had an exponential curve, well, the formula for an exponential curve is a times e to the bx, okay? Again, two numbers drive the whole thing, the amplitude and the rate, okay? And again, that's a parametric description of data. So parametric models, such as straight lines, quadratics, exponentials, all of which we can fit, and we will, are very compact, possibly wrong, but people prefer simplicity, right? So if this was a straight line, and I'll show you in a minute how to turn it into a straight line, it's dead easy. If it was a straight line, most people would be pretty happy if we just moved straight to fitting that straight line and using that as a model. So let me show you, for example, what happens if I plot x versus log y. That looks pretty straight suddenly, okay? And I'd be pretty happy to fit a straight line to that. So that's where we're headed. Now we're going to go on a journey to get there. So that's parametric statistics, okay? And we're all pretty familiar with how that's going to work. We're going to have a model, we're going to fit that model using least squares, and we'll talk about least squares soon too. And then we'll have a predictive model we can use, all right? Okay, what's the alternative? Let's go back to the original plot. The alternative approach is called a non-parametric approach, and the word non-parametric is actually a very bad description of what it is we're going to do, okay? Now, the best idea I can give you about how non-parametric is going to work is it's kind of what you do with your finger when you trace out for me what the curve's going to do. You follow the data along. When the data rises, your finger rises, and so on, okay? And if this took a downward turn, your finger would follow the data back down as well, right? So non-parametric is basically you put your finger at any x where you think the middle of the data is, and then you move it along as x moves, and you adjust where your finger goes depending on the height of the data points around that value of x, okay? And so you do something like that. Now if you think about it, what we're doing is we're tracking for each point where your finger is along that x-axis, we're tracking what the y is. So for every x, you get a y, and that y happens to be the height of your finger off 0, okay? And it can do all sorts of things. It's not restricted to be a straight line, so it doesn't have to go up linearly. It can jump around like crazy. And so if you tried to think of this in a parametric context, for every x, you're going to give me a y. So this is like an infinitely parametric approach, right? Because if I say, what is the value of hormone when x is 6.5, you give me a y for that. It just happens to be where your finger is at that moment, okay? And so for every x, there's a new parameter, which is where your finger is, and that's the y. So non-parametric, badly named, because it's actually infinitely parametric, okay? We call it non-parametric because it's not parametric, so it's a bad name. All right, so we're going to take a bit of a journey to get towards a non-parametric estimator. So here's a simple approach that's pretty simple and based on the way we did histograms. So there's my original plot, okay? Now I'm going to run through, and again, don't worry about the R code. I just want to show you sort of proof of concept here. Okay? So again, don't worry about the R code, it's not important. So what we've got here is we've got our picture, and what I've done is I've sliced it up. I've said, let's divide this range into bins. So I've got the X range here, and I've divided it into bins. The way I've divided it into bins is I've said, well, I want to have a reasonable number of points in each bin. So I ordered the data, okay, and then there's 92 data points. I'm going to have 6 bins. That's my choice. I could have more, I could have less. I'm going to have 6 bins. So the first 15 data points go in bin 1, the next 15 data points go in bin 2, and so on. So I'm kind of doing what I would have done with a histogram, just putting a set of bins down and seeing where the points drop. But now I'm doing that in 2 dimensions, okay? So I'm putting a set of bins down on the x-axis, and then within each bin, I'm going to represent the data by a box plot, okay? And so my basic idea here is that if I have really narrow bins, inside those bins, the data shouldn't be moving too much. It should be roughly stable. And I can represent that bin through its mean or median. Okay? So if you say to me, where is y when x is close to 0, you just take the mean of the points where x is close to 0 or the median of points where x is close to 0. So that's all I'm doing. And then I move across a little bit and I'm looking at this little slice here, right, the second slice. And in the second slice, if I said to you, what's the value of y in this slice, you might take a mean within that slice and so on. Okay? Now nobody does this. But this is moving us towards a non-parametric approach because what I'm ultimately going to do is create what's called a running mean. Okay? So as I move across, I'm going to have a little window. This should start to seem familiar to you, right? Because with histograms, we had a fixed set of bins. So here I've got a fixed set of bins. Inside each bin, instead of counting the points in each bin, which is what I do in one dimension, I'm just going to create a little representation of the y's using a box plot. Okay? Now, what I'm going to do is I'm going to go back, redo this plot. So that's what I'm heading towards. What I'm going to do is go back and redo this plot. When I do the plot, I'm just not going to put the points on this time. So I'm going to use type equals n. Points are gone. But then I'm still going to add those box plots. Okay? So, because the points just get in the way at this minute. Because all I'm doing here is I'm saying, well, this is now a description of my data, but I've taken the data out so you can't see it anymore. Now, have a look at this and think about what you did with your finger yesterday when you described this data. Right? Yeah, well done. He's doing it. Awesome. Start at the left, fingers are close together. As you move to the right, fingers get further apart. That's what's happening to the box plots, isn't it? If you go from middle to the middle on the box plots, they're flat and then they start to rise, yeah? So middle to middle, and that's a picture of what's going on with the data. And then remember, box plots have that box, right? So it's got the middle half of the data, and you can see that they're small down here, and then up here they're really big, and you can do that thing, right? So this is our first attempt to summarise this two-dimensional data using slices, little slices, okay? And it's like a histogram, but it's like a two-dimensional histogram. Inside every slice, I'm representing the y's using a box plot. Now, let's be clear. Nobody does this, okay? This is just part of our journey towards understanding what you could do and what we will do, okay? Now, what's going on here is that within each slice, I'm representing what is a lot of data, essentially by 5 numbers, but principally by the 2 quartiles and the median. And if I'm only worried about location, I only need the median, okay? And I could just join the medians. I'd get what's called a median line, and I would get a picture of where the data goes. All right. Now, I could play around with these slices. I could have lots of slices, or I could have very few slices, okay? If I have just one slice, and I represent that whole thing by the mean, I just get a flat line. And that's terrible. It doesn't describe the data at all. Okay? If I have lots of slices, right, between 0 and 25, instead of having them spaced apart, about 5 apart, if I made them really narrow, all right, the line's going to jump all over the place because the median is not going to be very stable. I'm going to get a very bumpy line. Okay? Now this should start to look to you like what we did as we moved from histograms to talking about densities. Remember what we did? We had these bins for histograms, and then we said, oh, let's turn the bins into little windows or kernels. Let's give the kernel a shape, right? Now let's drag that shape across. The shape's got a width, okay? And when you're inside, in a histogram, all you did was you essentially did a weighted average of the number of points that were in the window, and the weights were equal to the value of the kernel. We can do the same thing now in 2 dimensions. What you do inside each window is not just count the points, weighted average. You actually look at the y's and do essentially a weighted average of the y's. Okay? So that thing's called a kernel smoothing. A kernel smoothing. So let's do that. There's a command in R that does it. Okay? So we're going to do it for the data on the original scale. So plot x and y. There's the data. Lines Now, the command for kernel smoothing is k-smooth. K-smooth. Not like K-pop, pop music from Korea. This isn't smoothing from Korea. K here stands for kernel. Kernel smoothing. Okay? K-smooth. You give it X, you give it Y. What else do you need to give it? All right, well, before we complete this line, let's ask for help. Because I want to get you into the habit of asking for help. Well, let's do help on K-smooth. Let's see what it tells us. So over here, help has appeared. So first of all, it tells you who were the two statisticians who developed this. Two guys named Nadaraya and Jeff Watson. Jeff Watson was Australian. Okay, so Australian statistician. K-smooth XY. Then you've got kernel equals. You've got two choices of kernel, box or normal. Then bandwidth equals, and that's the width of the kernel. Now, this is where, for a moment, we sit and we grumble because there's no consistency between the options names in R, right? Because in density, you had density of X and then you had window equals or kernel equals, right? That's cool. Then you had width equals, okay, to get the width of the kernel. And for densities, you had a choice of, something like 7 kernels, but there was rectangular, R, Gaussian, G, triangular, Epenichnikov, cosine, etc., right? Well, for K-smooth, the option's called kernel, so that's cool. You only get two choices, rectangular and Gaussian, but they call them box and normal. Well, that's fine. I mean, rectangular, right? Rectangular, it's like a box, so okay. Gaussian, well, we know the Gaussian curve is the normal curve, but, you know, why on earth couldn't they just use the same damn name so it'd be easier to remember, right? And my simple answer to that is because this is not a Microsoft product, folks, okay? And when you open a Microsoft product, you know what's going on. Even if you've never opened it before, File menu, under File, New, Open, Save, right? Under the Edit menu, you know, cut, copy, paste, you know exactly where they are, you know exactly what the shortcuts are. They're the same in every piece of software because someone in Microsoft looks at it and goes, let's make this a consistent experience for everybody. You might hate the product at the end, but you can't complain that it's not consistent because it is. That's not the way R works, okay? R is literally written by hundreds of people, right? People write their own functions and they add them to R, they write their own packages and they add them to R. But even in the base package, this is part of the base package, right? Functions which do ostensibly similar things have all sorts of different names for the options. And this creates a problem because it's hard to remember stuff, right? So you have to think to yourself, I'm using density, okay, it's window equals and it's R or G or T for rectangular, Gaussian, triangular, etc. Got lots of options. As soon as I move to K-smooth, they're the same shape of kernel, it's just they've got different names, box and normal and so on. That's why using help is necessary in R, because there's no consistency. And unlike Microsoft, you can't even write and complain. Who do you write to, right? So it's no good. So you just have to learn it. You just have to learn it. Okay, so these are our options. So let's do it. Let's go. So let's put the plot back on the page. By the way, in this thing here, you can see plots are under this tab, so that plot's still there. Okay, so I go lines, K-smooth. I give it X, I give it Y. Okay, so it's kernel equals. So I've got a choice of box or normal. So let's go box, B. You can use the first letter, you don't need to type the whole thing. Kernel equals B. Bandwidth, which is what it calls width. Bandwidth equals. Now, I'm going to choose a small number for bandwidth at the moment. Bandwidth equals 1. Okay. And then LTY equals 1. So I'm going to add just a black line. There it is. There's my kernel smooth when I have a really small bandwidth. Now, I deliberately chose a small bandwidth so you'd see how bumpy it is. Right? See how bumpy it is? And not only is it bumpy, it's got gaps. And the reason it's got gaps is because that window is so small that sometimes there's nothing in it as it slides across. So what it's doing is you've got this little window, it's a little box window, so it's a little rectangle, right, little weight function, looks like a little box, and it slides across from left to right, and what it's doing as it slides across from left to right is it's calculating the mean of the y's that are inside it. And then it's just joining the dots as it moves across. That's all it's doing. And as it moves across, sometimes, because there's a bit of sparsity in the data, there's not much in the window. And you can kind of tell that because you can imagine this little box window starting here on the left and moving across. Right, the data here is kind of dense in the x direction, but here there's a bit of gap, see? And the box actually fits entirely inside it, and so it's trying to average nothing. You can't average nothing, right? So it's got a gap, gap. Look here, there's not a gap, there's just one point in the box. See how the line goes straight through it? It has to, because it's averaging what's inside the box. That's all that's inside the box, and so on, okay? So that's a box kernel. And it looks jerky, right, because it's just a straight average. All right, let's redo, but now let's up that bandwidth. Let's make bandwidth 5, okay? And it's getting better. It's getting better. It's smoother. Still not great, but it's smoother. And again, sparsity in the x direction is causing us a trouble because basically you can see what's happening. The box is moving across. It's slightly wider. Suddenly, a whole bunch of points up here enter the box, and they drag the average up, right? And so this line is sort of meandering along here, responding to these points. And then all of a sudden, these ones up here enter the box and straight up. Okay? Straight up. And then once those points are in the box, they take a little while to leave, and so it flattens out again. So it's not great. All right, let's do again with even bigger bandwidth. Let's go bandwidth is 10. And that's sort of the best you're going to do with a box kernel. Okay? So it's jerky, and that's because it's a box kernel. So box kernels have hard edges. So points enter and leave abruptly. Okay? And that's about as smooth as you're going to get with a box kernel. Now, one thing that's always important to wonder about is how do you choose the bandwidth? And again, there's no rule that's going to work every time. But what I usually do is I take the range of x's, okay, which is here 25, 0 to 25, and I divide it by 3, just to get a rough cut, okay? Just to get a rough cut. So 25 divided by 3 is 8 1/3, so I use 10, okay? I use 10. All right, so let's try the other kind of kernel shape. So plot x, y, k-smooth. So instead of kernel equals b, which is box, I'm going to use kernel equals n, which is normal. Again, if I choose a small bandwidth, I deserve what I get. It's going to look pretty jerky, but not as jerky as the box. Okay. No gaps. The reason there's no gaps is that the support of a normal distribution is infinite. So you always get a weight, right? A box kernel, the weights are 1 when you're inside the box and they are 0 when you're outside the box, right? For a normal curve, they rise to a peak at the middle of the curve, but they never go away completely. So the thing never actually has a gap. But you can see it's, you know, there's a roller coaster. And you can see when the box is narrow, it goes through this point and more or less through this point because it has to. They're the only points in the window. And you've sort of got smoother behaviour around here. And as I increase the bandwidth, you'll see, I'm just going to add another one here, 5 on the same plot. Just make it a different colour. Okay, so that's with bandwidth 5, and you can see it's much smoother. So normal kernels are generally more smooth. And if I rack that up to 10 and I make it green, you can see I'm getting a pretty good model for what's going on with this data, okay? And if I'd said to you, use your finger and show me where the data goes, that green line isn't terrible. Now, apart from probably here, right? Because I'm guessing if you were using your fingers when you were heading off the right edge, you're still going up. Right? Okay. So that's called an edge effect. Kernel methods suffer from edge effects because when that window departs the right edge of the data, there ain't nothing to average. Okay, so it averages fewer and fewer points. So this can wiggle around a fair bit, and it's dominated by what's happening on exit, right? So you'll very often get edge effects in kernel smoothers, one of those things. But let's talk about the edges, because it's important to talk about the edges. So here we've got a statistical model that relates blood loss to hormone level, okay? Now, before I showed you any of this stuff with normal kernels and all that sort of junk, and I just got you to use your fingers, everyone did this, right, down the bottom, and up. And on exit, still going up, right? Okay. Now, on the left-hand edge, there's nowhere to go. If I said to you, continue on the left-hand edge, you would rightly say to me, you cannot induce less than 0 blood loss in a rat. Well, you could pump blood into it. No, too horrible to consider, right? So you know, no one tries to go off this edge because it doesn't make physical sense, right? Truthfully, neither does this. How much blood does a rat have, right? I mean, if you extrapolate this out to 50, I mean, that's one big rat. And I'm guessing that's just not going to work, right? Okay, so what you do off the edge, even if you think it's continuing to go up, probably doesn't make a whole lot of sense anyway, right? So that's point number one. If we were fitting straight lines or exponentials, it would keep going up. The model would keep going up. But you know what happens when you get off the edge of your data? No, you don't know what happens when you go off the edge of your data, is the answer, right? So the way to think about data is, it's like you've got a camera, right, which for everybody these days is a phone, and you're at an event, so you've got your phone and you're putting it on something you want to take a photo of, right? Now, immediately to the left or to the right of where you're taking the photo, there could be someone naked. Could be, right? But you won't know that if all you're looking at is through the viewfinder, okay? So, the data you have is the entire world. It's all it can tell you. It can't tell you anything off either edge, and you can't look, right? And so, one of the big ticket items in data analysis is extrapolation is extraordinarily dangerous, okay? Which brings us back to something we were talking about earlier, right? Climate change. How high is the temperature on Earth going to go? We don't know. The models say it's going to keep going up. We don't know. We don't know. My best advice is wait till next year. Then you'll find out, right? But all that's saying is you'll get more data. And so unless you can get rats who have more blood, you don't have any business guessing what's going on out here. And so edge effects aren't as bad as you think, because sometimes they're really an acknowledgement of the fact that beyond here you best not be guessing. Okay, so that's kernel smoothing. Now, what is kernel smoothing doing? It's doing local averaging of the y's inside the window as you slide it across from left to right. Okay, that's what it's doing. Now, there's an alternative to doing local averaging, and it's pretty cool. So people do use kernel smoothing. It was very popular in the 1980s, right? Then a guy named Bill Cleveland, who was at AT&T Bell Laboratories in the United States, came up with this new method. And it's called LOWESS, which is spelled one of two ways. It's either spelled L-O-W-E-S-S or it's spelled L-O-E-S-S. So sometimes the W goes missing depending on who you're talking to. And I can tell you where the W comes from. So LOWESS, I'll type it here. L, local. So L stands for locally. Actually, I should make the O capital as well. L-O. And I'll put the rest in brackets. Locally. And the W is for weighted. And then the first S is for scatter plot, and the second S is for smoothing. Now, if I hit return now, R is going to give me a hella error because it won't have any idea why I've just typed that. So, but that's what low S stands for, locally weighted scatter plot smoothing. Okay? And its acronym is, as you can guess by all those capital letters, not LOPWES, low S. Okay? Now, by the way, if ever you want to type something into R and not have it actually evaluate it, put a hash in front of it and it'll ignore it. Okay? Good programmers, when they program stuff up, put lots of comments in so that anyone coming in behind them can actually understand what on earth they're doing. So if you see well-written R code, there'll be all these hashes in there showing you what people are up to. Anyone who's just programming for their own pleasure generally just ignores all that. Regrets it 6 months later when you come back and have no idea what you did, but that's the way life is, isn't it? Okay. Every time I discover something important in my life, I make a note, oh, this is really good, I now know how to do this, and next time I have to do it, it'll be fine. But then the next time I have to do it, I always have to relearn it, right? And, you know, I can tell by the couple of people nodding that this is not an unfamiliar experience. Eh? So, okay, how does low S work? So the command in R is low S, L-O-W-E-S-S, okay? So what do? We do what we always do when we don't know how something works. We ask for help. Low S, scatter plot smoothing, locally weighted polynomial regression. Okay, so what's it doing? It's taking a window and it's moving it across the page from left to right on the scatter plot. And inside the window, it's calculating, it's fitting a little polynomial, a little curve. Okay? But it's doing something else. It's a little bit different to what kernel smoothing did. With kernel smoothing, the width of the window doesn't change. It's always what you say it is. So if you start off with width equals 5, then all the way across you've got this width 5 window dragging across. So it's what's called a fixed bandwidth smoother. Okay? Now, we discovered by looking at our example that fixed bandwidth smoothers have the weakness that if there's sparsity in your data in the x direction, there can be gaps, right? Windows in which there's no data. So that's a problem. Low S tackles that by using what's called variable bandwidth smoothing. It lets the window grow and shrink depending on how sparse the data is in the x direction. So instead of saying width equals and giving it a number, which is the physical width of the window, it uses an option called f equals, which is the proportion of data that's in the window. Okay? And the default is 2/3. So it says, I'm going to have a window and I'm going to make it wide enough to incorporate 2/3 of the data as I drag across. Okay? So that's what it does. So the format is low S xy, f equals 2/3, and the rest is just junk, right, that you don't need to worry about. F equals 2/3 is the smoother span. This gives the proportion of points in the plot which influence the smooth at each value. Okay? So the default is to have 2/3 of the data in the window at any moment as you move across from left to right. So let's do this. Let's run it and see. So we start with plot xy again. There's my original data. Okay, lines, low S, xy. Okay, I'm going to use the default, f equals 2/3. Okay, so the syntax is really simple. There's the curve. That's the low S curve. Now, there's a lot of points in here, down the bottom, right? Because it includes all the rats who had 0 blood loss, the control group. So, as your window starts on the left-hand side and moves across, it's tiny. And it's tiny because there's a lot of points down there. 2/3 of the points are down there. When it moves off them, the window gets wider. And when it's up this end where the data's sort of spread apart horizontally, the window's quite wide. So it accommodates sparsity in the x direction by growing and shrinking the window appropriately. Now in this case it only grows it because the data sparsity only increases as you move from left to right. But it's really easy to construct a data set which is dense in different spots and sparse in other spots. Low S just works it all out. It just says, right, 2/3 in the window at any moment and so on. Now you can force it to be jumpy by using a much smaller proportion, right? So I can do the plot lines low S, X, Y, but if I go F equals 0.01, so in other words I only want 1% of the data in the window at any moment, I get exactly what I deserve. Join the dots. Okay? Because at any moment there's basically only 1 point in the window. Okay? Why did I choose 0.01? There are 92 rats. Okay, 1 in 100, so it's basically allocating 1 point to each window. Okay, if I raise that slowly, 0.1, it gets a bit smoother. I'm just laying these on top of one another so you can see. 0.3, it's pretty smooth by then. Now let's go nuts. 0.99, you can see we're starting to lose features, right? It rises more steeply, more quickly, because when I put F equals 0.99, these later points here are in the window right from the get-go. So the average is rising, right? Now, this is a piece of code for which the default seems to really work. F equals 2/3. I almost never have to mess with that proportion when I use low S in real life, ever. That doesn't mean it will always work, because you can work to defeat it, right, by having data that's got ridiculous features, but generally speaking, that'll work pretty well. So, low S. So there's the default. It's pretty good. Okay, I'm just going to put the default on, and I'm just going to put that one on which has very, very high F, but I'll make it red. Okay, you can see the difference, right? The difference is all here, and it's there because what's happening is this line here, the black line, is not being influenced by these guys, right? Because they're not in the window. Okay, but when I make the window artificially large by insisting that most of the data has to be in it most of the time, these points here are actually dragging that line up, and that's why it's north. Okay, so it's all good. Okay, now K-smooth and low S give you non-parametric curve estimators. Okay, they're both non-parametric methods. What I would like to show you is how they compare with one another, right? So let's do that. Let's go back to the original plot, plot XY. Then I'm going to put the K-smooth line on. Okay. I'm going to use a bandwidth that I think is about right. So I think a bandwidth of around 10. I'm going to use a normal kernel. Okay, so the K-smooth's in green. The low S is going to be in red. Okay, so you can see the difference. Now, I've chosen a good bandwidth for the kernel estimator here, but it's a fixed bandwidth. So you'll notice that where the data is relatively dense, the window width isn't a problem. And so the low S curve and the K-smooth curve are pretty much right on top of one another. Where the normal curve starts to struggle, where the K-smooth curve, I should say, starts to struggle, is where the data starts to get sparser horizontally. And you can see it ends up doing this, whereas the low S curve is able to more or less deal with that. The other thing about the low S curve, which I haven't told you yet, is that it fits a local polynomial, but it actually doesn't use least squares. It uses a robust fitting method that is better at dealing with outliers. And so it's not going to tend to be as influenced by outliers as the normal curve. This normal curve here is basically, the reason that as it exits, it's starting to head down, is that guy there. That guy there. Right? One rat caused all that trouble. That dirty rat. Actually, it's a bloodless dirty rat. Okay. So, someone sent me an email yesterday quite sensibly telling me that my lectures tend to be cut off in the recording because I never can finish on time. So today, I shall finish on time. That'll do us.